We work, we live, we innovate, and create. At the center of it all is your brain health. The ability to solve problems, think analytically, share empathy, and thrive.
We're trying to make brain performance really the next fitness revolution.
Scientific discoveries show that your brain can adapt and grow regardless of your starting point. The Center for Brain Health can show you how to transform your mind to work stronger and faster.
We learned from a national poll that 95% of people want to do something about their brains. The problem is they don't know where or how to start. At the Center for Brain Health, we have easy-to-use, scientifically proven tools to provide people a proactive path to do just that, to help people everywhere improve their quality of life through brain health. What's exciting is that it's easy to start, and starting is urgent because we are in a brain health crisis.
So how do you boost your brain power? How can better brain health help you focus on what's most important?
Brain training is a part of the way that we would distinguish ourselves from others. Quite frankly, I think it's going to be commonplace in businesses in years to come.
We are seeing an epidemic of mental health concerns. Stress and overload lead to depression, anxiety, and burnout. Our brains hold the key to navigate these hurdles. It's never too soon to start.
I think the greatest national security threat is pre-K through 12. If we don't take care of educating our young men and women, then we have to ask ourselves, where are we going to be in 20 years?
Research shows training middle schoolers how to think, problem solve, and innovate significantly improves academic achievement. Even more importantly, it enhances confidence and well-being for them to thrive throughout their lives.
It really helps the kid and it builds their stamina. I genuinely credit my success in the classroom from this program.
The key to the future is stronger brain health for individuals and communities. Ready to transform the world with us? Be a part of the brain health revolution. It starts here.
Welcome, everyone. We're so excited that you're here today and you're in for a special treat. Welcome to Frontiers of Brain Health, where we want to dig in to the most exciting advances in what's making our brain stronger, but also what can go wrong, and find some of the neurobiological mechanisms of what can go wrong. My name is Dr. Sandy Chapman. I'm the founder and chief director of the Center for Brain Health and a professor in the School of Behavioral and Brain Science. Our vision is to define, measure, enhance brain health for people regardless of their starting point. Right now, we are in every single state, 43 countries, and we've just begun. So we're glad that you're here and that you want to be part of where we're going to make your brain stronger. For those of you that are online, we will have some question answer. Just use the Q&A code to type those in terms of what's going on. The Center for Brain Health is a cognitive neuroscience research institute where we're implementing discoveries at the earliest time possible. It is now my great pleasure and honor to introduce Dr. William Bill Dauer, who is, many of you have heard of because they have been, I feel like he's the long-awaited savior for what has been exciting for this inaugural Peter O'Donnell Jr. Brain Institute. He is a professor of neurology and neuroscience at UT Southwestern Medical Center. As a neurologist, his research in dystonia and Parkinson's is really changing the way people everywhere think about what Parkinson's is. He received his medical degree from Washington University, wonderful, incredible, esteemed in St. Louis. After completing that, he was at Beth Israel in Boston, where he became a neurology resident and fellow at Columbia University. He pursued his postdoctoral work in Columbia in Renee Henn, who is very well known for alpha-synuclein, which, as we know, there are many causes to Parkinson's. So looking at different things that can identify some of the toxin exposures. For nearly 2 decades, he's been doing groundbreaking research in the molecular basis of it. You know, when you think about Parkinson's, we think about the progression of dystonia and the irregular movements. He is looking at what those mechanisms could be. Or we think about the falls that are very difficult to treat. He's looking at the neurobiological causes of that so that treatments can be developed. We are so excited to have such an incredible neighbor, amazing new Texan. So he is now declaring Texas his home, and we welcome him with big arms. Please join me in welcoming Dr. Bill Dauer.
So first of all, Sandy, thank you very much for a super generous introduction. And thank everyone here and online for taking the time to spend some time today to hear what I have to share. Today's talk is a little bit of a hybrid. What I'm going to do today is sort of a couple different things. On one hand, I really wanted to share with you, and Sandy and I talked about this, the sort of vision for the O'Donnell Brain Institute. So at a high level, what are the kinds of things that we're doing? What are our goals? And so that's not so much a science talk as a institute talk. And then I'm going to transition, as Sandy indicated, to the work that I've been doing in the lab for the last 20 years. And I am going to focus primarily on, and I have to confess, a sort of a cell and molecular person, so a little different than what you all do here. But I think I hopefully can share with you the kind of ways we think about that work. And primarily I'm going to focus on the symptom of dystonia, which is something that can happen within Parkinson's, as well as in other contexts. And I just want to try to illustrate how we go from a molecule and eventually kind of get back into brain imaging and the patient, ultimately, which is what we all care about. So let me just begin by stating something that we all know, which is, of course, brain disease is affecting all of us, either directly or indirectly, unfortunately. And really, one important point to make is that the heart of the mission of the O'Donnell Brain Institute is sort of a commitment to take on really the breadth of illnesses that affect the brain, from autism to Alzheimer's, brain tumors, treatment-resistant depression, and many other things. We're really all which is in our purpose. What's critical is in addressing these different diseases to do so utilizing really the broad spectrum of tools that are available. And so that, in no particular order, includes working in the labs to understand, as Sandy alluded to, the sort of root causes of these problems, transitioning from discoveries to trials and investigations with our patients, and also, and as important as anything else, working to the development of new models of patient care for patients who are suffering today. We can't wait for the big discovery 10 years from now or 15 years from now. And the structure of the Brain Institute really reflects this mission. So just to kind of give you a little sort of organizational chart in a little prettier form, the Brain Institute consists of all the major brain departments, so neurology, neurosurgery, psychiatry, and physical medicine rehab, as well as our neuroscience department. So really, right there you already see an integration of clinical and scientific departments all under one roof. And everyone within these departments are members in the They benefit in various ways from that. But as I came, the other point is these problems are larger than what lives in these departments. And so the Institute also embraces the entirety of UT Southwestern faculty. So those who are in these other departments, and these are not, this is just examples, it's inclusive of all, those in these other departments, be it immunology, which is a very important new frontier in neuroscience, those faculty who work on a brain-related project or topic can apply in a simple way and become investigators, and we can help them in various ways to integrate them with the community and really use the full force of all of our faculty to approach these problems. And this is really important because, and I'm sure this is something you all think about often, no clinical problem really maps to a single department, right? To take Parkinson, when one has Parkinson's, they have movement problems, but they may also have problems with mood, problems with emotion. They need a physical therapist. I mean, so there are many, many elements that have to come together in order to optimally treat patients with these illnesses. And similarly, scientifically, they don't live in a particular department. Departments are something that humans devised in order to organize ourselves, but these problems really cross boundaries, and it's through this interaction we think, not only, of course, you need excellence in all this, but that interaction is something that's really important. That's really at the heart, the DNA of the Donald Brain Institute, and to bring these folks together. So overall, we really have three broad missions. Destination clinical care, and I'll talk a little bit about that. The science, of course, and as well as our community. So in terms of clinical care, we're really assembling large teams of physicians, nurses, therapists, other providers in key areas to provide sort of ecosystems of care that are really more effective and more collaborative, and as I was alluding to earlier, allow to the extent possible a sort of one-stop shop to help a patient get all the care they need in one place, as well as if the providers are all there, they can also collaborate and be more effective in how they approach the patients. I showed you an example of our spine center, but we are developing these multidisciplinary ecosystems in a whole variety of these illnesses that I show here. And it's not exclusive to these, but these are ones that we're focusing on as initial priorities, as you can see. Now this model includes an important concept that when we think about clinical care, we really embrace the vision, which I know to all of you, especially Sandy will speak to you, this idea of wellness, not illness. So we have actually dedicated some of our philanthropy beyond what typical providers would pay to develop this so-called total care program to bring additional resources to these clinics, things like navigators, things like family education, counseling of various sorts. So again, just giving the picture of a type of care that is different and we think is really particularly important for brain disease. Certainly it's nice to have that in all illnesses, but brain disease in particular affects so many, essentially all aspects of our lives and our relationship with our families, that this is particularly important. And unfortunately at this point, society, the payers and so forth haven't really recognized this, and so we're trying to sort of step up in this way. It's also important, as I alluded to say that our focus on the patient also extends to a really robust program of patient-centered research. So we have a large, dedicated team I'm showing here that was made possible by a very generous gift by the Perot Foundation to fund this Neuroscience Translational Research Center. So this is a team that's dedicated to all the studies, most of the studies in neuroscience that touch patients. So whether it's doing the kind of imaging that you all do here and tracking how, understanding a particular aspect of how diseases progress to understand them better, whether it be interventional studies of a new drug, whether that come from inside or we do a lot of collaboration with pharma in helping them test their drugs. All of this activity goes in, is taking place in this, what we call the NTRC. And there's currently about 125 separate studies going on in a diverse range of disease areas from this team. I'll just highlight one particular big umbrella point that I think is really important in this clinical research. It's becoming increasingly clear that really for nearly every common disease, that really there's different groups of patients with distinct characteristics, and it's really important and a big part of the mission now in brain disease generally is to try to understand what these different categories of patients are, because they may respond, and there's evidence to this, differently to different treatments. So I'll just take, since Parkinson's disease is the sort of subject I know the most about, there really in some ways is not a Parkinson's disease. There are Parkinson's diseases. Some people have certain genetic risk factors. Many people don't. There are different paths that people take, and understanding early on who's going to go down what path and what's best for them is something that NTRC and we generally are very interested in. It's a very important aspect of what we do. For another reason I'll highlight, which may not be apparent, if you do a clinical study on the whole group of many different causes, the drug may work for a few of them, but not others, and you maybe won't see that. But if you can target what you're doing and really look at a particular group or a particular therapy designed for them, we're more likely to identify things that work for particular groups of patients. So that's really important. Now, just as this clinical care and clinical research requires a huge multidisciplinary type of approach, so do our laboratory programs, which that are really, now I'm shifting into those programs that are aiming to identify the root causes of brain diseases. That can be, that the goal of which is to target the sort of root molecular causes of these diseases and to slow or hopefully prevent them in the future. So I'm just showing one example, the most well-developed example on our campus, which is the Center for Alzheimer's Disease and Alzheimer's and Neurodegenerative Diseases. And this center, which currently has about 60 different people working, scientists working in about 6 different groups, they're working in all of these different areas together, all with a common goal, but looking at the problem from distinct ways and collaborating. And so this is a sort of model for how we're developing some of our signature scientific areas going forward. And I'll show you a picture in a bit about our new building. I just want to, and the vision is to nucleate some of these really high-profile, most important programs into that building. There's, beyond that, there's a wide range of molecular research that's going on across the Institute. I'm showing here, this is actually a picture of the atomic structure, the molecular structure of the GABA receptor. This is a receptor in the brain that's critical in terms of mediating what's called inhibition or dampening brain activity. And so much of brain activity is an important balance in all these different things between excitation and inhibition. And the Hibbs lab discovered and published the structure of this. And the reason this is important, it's not just a pretty picture, which it certainly is the shape of this receptor allows people who design drugs to actually design chemicals that would fit structurally into place to modify it in particular ways. And this is, I just use as an example of a lot of the molecular work going on. And just to say that we sort of foresee a lot of future development in genetic therapy and immune therapy, and we have dedicated programs in both of these. The Perot NTRC, which I mentioned just a bit ago, is actually in the process currently of testing a novel gene therapy in children for an inherited genetic disease, which is first of its kind in the country. The immune angle is also very important, and we're involved in a variety of recruitments to develop a program in neuroimmunology. So it's become very clear over the last 10 to 15 years that the link between the immune system and the brain is critical for normal function, but of particular interest in terms of brain disease is really quite an important player in the progression of Alzheimer's disease and perhaps other neurodegenerative illnesses. That's also important because any of you who watch television have seen these ads for psoriasis, Skyrizi, and all these things, or you've heard about these cancer treatments. What these actually represent are a great advance in biomedicine generally in the ability to manipulate the immune system, which we have, it's an old field, and so there's a lot known. So that provides some hope that understanding the role of the immune system in neurodegenerative disease can piggyback, if you will, on this understanding of how to manipulate that system and help. Y'all don't need any introduction to this. This is a slide I like to show, and this is sort of bringing coals to Newcastle kind of thing. But we're also very interested, if we go away from the molecular, on the what we call circuit neuroscience, right? So how does, and which is the goal of a lot of the research that goes on here at the Center for Brain Health, how does information get transferred between brain areas? And I put the chessboard up there because it's, I kind of like the analogy is this is about the rules of chess. The molecular work is trying to understand what holds the pieces together at an atomic level. That's a separate kind of question. This is a so-called higher level question. It's a different way of thinking about brain disease and a really critical way of thinking about brain disease. And we have in our neurology, neurosurgery, and psychiatry programs, we have faculty across the Institute that are assessing brain function in a whole variety of ways, both non-invasively with things like EEG and magnetoencephalography and other things, but also we have a very active what's so-called functional neurosurgery program where during brain surgery, the neurosurgeons are actually able to record brain activity, and that's looked at by them and by neuroengineers, biostatisticians and things, to try to understand how these circuits work normally and critically when they're abnormal, how we can modify them to suppress brain symptoms of illness. And the kind of flip side of that is, in terms of how to act on that information, is this field called neuromodulation. And I'm showing you 3 different areas here, all of which are going on our campus. I'm going to show you in a little bit an example of high-intensity focused ultrasound. Deep brain stimulation is something that happens already in diseases like Parkinson's and Tremor, where an electrode is placed in the brain and it stays there. Or, it sort of stays inside the body, and there's an electric little battery that sends an electrical signal. And it's because of understanding, because of the basic research of understanding how movement circuits work, physicians and scientists over the last 40 to 50 years were able to identify where that electrode should go and what kind of electricity to be there in order to alter that function and help people, particularly with Parkinson's disease. But let me tell you a little bit about HIFU, which is just the new and really particularly exciting. So what this is, if you just think of a magnifying glass, burning, when you're little, at least us boys probably, burning leaves with a magnifying glass. So instead of focusing light into a point, what high-intensity focused ultrasound does is focus sound waves from 256 little ultrasound generators into the brain in deep structures. And it can focus that sound waves at one point to a size of about a half a grain of rice. And again, knowing these circuits, we know that for certain things like tremor, certain kinds of tremor, if you make a small lesion there, you can basically disrupt that tremor circuit and improve the patient. So I'm going to show you a short video of what this can do. This is happening every week. Not only it's happening here every week, it's happening across the country as well, at some number of places. So here's a patient you're going to see here with what's called essential tremor. This patient has suffered with this disease for decades, and here's how they look as they try to write a spiral or try to hold their hand still. So it's pretty obvious that that's a disabling thing. So again, let me emphasize, no neurosurgery. You wear something, you go into an MRI, it takes 45 minutes, and then you leave like this. And that is for life. So this is just the beginning. We foresee that we have a so-called preclinical program to see how can we advance this in other areas, other illness, other symptoms, and so forth. And I'm happy to, after we can answer questions about that. But this is a technology that we're very, a lot of high hopes for, both for this type of study, but it's also something that can be used when it's tweaked in a little different way to help get drugs into the brain that otherwise have a hard time passing through the blood-brain barrier. And so that's a whole other area of interest. And with the new biomedical engineering science department, which is a joint venture between UTD and UT Southwestern, they are very involved in and increasingly will be, so that's a really wonderful point of contact between the institutions. It's something that we're very excited about. Let me just end this part of the talk by talking about the community. So this is something, really near and dear to my heart, and the thing I was able to actually start, the day I got here. So we want to make sure that, number one, for the people who are here on our campus, they have the best possible environment, able to interact in the kinds of ways I've discussed. But we also always want to bring, being good Texan, we want to bring in new talent, right? And so, it's important when recruitments come, they see that this community has the environment, the resources, the capabilities that is a place that they want to work. So I'll just tick over a few things. So this is just a pretty picture to show you we're developing a variety of so-called research cores that have equipment that's too expensive, too large for any one lab to develop, and then the institute can purchase this equipment and run it and make it available to everyone in the institute. So this is just a so-called super resolution microscope. The big point is the normal is on one side. You see how much more detail you can see in this side. This just allows us to look in much more powerful ways and ask some of these more molecular questions that you otherwise can't. We also have developed actually a whole variety, and I won't go through each one of these, but a whole variety of programs that take into account both early learners, faculty themselves, innovative work, so these internal grants programs that we run, and there are many of them, and other workshops, for example, for new faculty to onboard them so they know how to write a grant, how do we do this, how do we do that. So it's not everyone learning on themselves, but it's by themselves, like I had to, but the institute and the institution trying to help to really advance people's careers and allow them to make those discoveries that we all really strive for. And one of the ones, this is just one, this so-called neuroscientist training program, which we're kind of excited about. And this is bringing the most junior people, those young, either MD, PhD, people who want to be MD, PhDs, or who want to do a PhD in neuroscience, help attract them into our program and give them both mentorship, develop a community of them, and also give financial support to try to get these early career. Because these problems are large. We're very hopeful we're going to solve some of them in the near term, but there are a lot of them, and we always need to have our eye on the ball of training that next generation of great scientists in order, because this is going to be something that is going to take a long time to solve. And then I'll just end this part of my talk by saying, of course, and we're in a gorgeous building here, and so we know buildings don't solve any scientific problems, but they help bring people together. They help attract people, and so they're actually very important. And so I'm showing you on the left side, that main building is the new O'Donnell Biomedical Research Building, which is the home for the laboratory, research of the O'Donnell Brain Institute. Actually, you can see off to the side there, Clemens, and actually the third tower of Clemens, which opened about a year and a half ago, is also the inpatient home of our O'Donnell Brain Institute. So all the neurology, neurosurgery, and psychiatry all are in brand new state-of-the-art space there, and actually that high-intensity focused ultrasound is located in Clemens. And you just see this beautiful lab space that we have within this. So let me, how much time do we have? I have a half hour. I'll leave some, yeah, it'll be fine. Yeah. Let me talk about the work that we do. So pretty much everyone will know this gentleman. Now you do, if you didn't before. And so, you know, he has Parkinson's disease. Oh, I don't know why that went wrong. He has Parkinson's disease, and what you saw is that he's doing a lot of movement. So he has what's called, and Sandy referred to as dystonia. So dystonia is a abnormal involuntary movement, and you can see it here. So it happens in Parkinson's disease. So you see this woman's foot turning and her hand going on her, and her neck being pulled over. But it also happens separately in other, this abnormal kind of movement also happens in other diseases. So it can happen what we call idiopathic for reasons we just don't understand, just spontaneously. It's a fancy word for spontaneous. But there are also genetic forms, and the genetic forms are particularly interesting and particularly valuable. So if we want to study a brain disease, genes are a really powerful way in because it gives someone in a lab an ability to understand what that gene does, what it does in the cell, what it does in the brain, allows us to make models, which you'll see. So it's really the entry point for all kinds of studies that you otherwise cannot do without understanding the genetic basis. And for dystonia as an illness, there are many genetic forms, and I'm just highlighting, the details don't matter, but we work on a couple of these, but I'm going to tell you about one of them, the first one called DYT1. DYT just stands for dystonia. And I just want to kind of show you the kind of logic that we use to kind of go through these kinds of studies. And just to highlight the rationale a little bit, we're studying this dystonia in this genetic form. It's not Parkinson's. The reason we're doing this is because in this case, in this abnormal movement, we can look at that particular symptom in a kind of pure state. So in Parkinson's, you got 20 other things going on, potentially. You have tremor, you might have walking issues. And so if you model that, it's hard to know in the brain what's connected to what. But the idea here is you're kind of plucking out one symptom with a genetic cause, trying to understand the mechanism of that, which of course is good for the people that have the illness itself, but also the idea is the principles there will be able to be used back in Parkinson. So what's really interesting about this particular illness is even beyond all of that. So in the patients who get this so-called genetic form of dystonia, they get one symptom. They get this movement abnormality. Their thinking is normal, their walk, everything else, their taste, vision. So, and we're showing here a glucose PET scan, so it just shows the red is where the metabolism is abnormal in the brain. The key point isn't the details of where, it's just to say that how is it that when you have a genetic mutation and the gene is all over the body, why do you get just one symptom? How does that work? If you think about it, it's not just a sort of theoretical question, it's all of illness. Why do you get Alzheimer's with those mutations or Parkinson with those? So beyond the specifics here, we're interested, as I work in a lab, is how do you get that specificity? What are the rules of that specificity? And I'm not going to talk much about that today, but I do want to say that that's important as a general concept. And and I'll show you, I always like to say, it's sort of like, it's like, how do you get dystonia is like a motor form of dyslexia. How do we think about these illnesses? And so by looking at these genetic forms, again, it might give us some clues to the rules of how one or another brain region is susceptible, and that might have larger implications. So let me just show you this particular illness that we're going to focus on here, this DYT1 dystonia. Let's see if it's going to go. This young boy started at about age 8, and you see his foot, just a little bit of turning in on that left foot. It's very mild. But here he is just a few years later. And now you see, not only is he bigger, he's got all kinds of movements, and he's very, very effective. So this is an illness that actually people start normal. Early childhood is normal. The disease begins, and it kind of develops over time. And then after about 5 years, it kind of stops. So it's actually another really interesting and important thing here. A lot of us here in this room, including, we were talking about Parkinson's, things about diseases of aging. This is also something about development. And what is it, I think Sandy could talk about, and many of you in the room could talk about, things that happen early in life affect what goes on later. And so this disease also is interesting in trying to understand what are the unique issues that are happening during neural development that can affect abnormalities that happen later. So I'll show you a kind of, this disease is caused by a mutation in a gene that codes for a protein called torsinA. The name doesn't matter. What you just really basically, I wouldn't worry about those details, but it functions deep within the cell. And we did a variety of studies early on to understand what you want to know when you have a genetic disorder is it cause the protein to act too much or too little? And we basically found out that this protein inactivated this gene. It made it work not enough. And so we developed a model, and I'm going to show you here in a minute, in mice by mutating this gene and reducing its function in the areas of the brain. This is a mouse brain on the side. So the back of the brain is over here, and the front of the brain is over here. And these are the motor areas where we kind of know from other things that are important in that disease. And so we were able to mutate it. So you actually can make an animal model where that one gene is just decreased in these areas using the sort of modern molecular biological tools. And lo and behold, what you get is an animal. Now we're holding the animal upside down because that's a motor test for them. The normal thing is to hold the paws out like this. But you see it's kind of holding them in and twisting like this, and then the trunk is twisting here. So essentially what we're doing here is developing an animal model that, with the same genetic insult or a similar genetic insult, that recapitulates it. And now we can use that to study the disease in the brains of these animals. And what we found is that these animals developed this in a very critical time window that's similar to children, so that replicates, sort of the illness. And similarly, it responds to drugs that are used to treat these patients. So let me just show you an example. Here's an animal before the drug. So it's got this clasping, which is abnormal. That's not what it should be doing. And here it is about 30 minutes after the drug, and now it's able to move more normally. So when we develop these animal models, what we're trying to understand is, does it look like the disease? Does it have the course similar to disease? And does it respond to the drugs, however imperfect they are? And since all those things are true, now we feel we gain more confidence that we can study this, and it's going to give us some insights. And basically what we found by looking at these animals is that they lack a particular rare type of nerve cell that makes a chemical called acetylcholine, these so-called cholinergic neurons. You would never see that on a so-called post-mortem or anything. It's only by having an animal model you're able to really see that. And so we made that discovery, and then, which is, I'm just going to go over this, and this is just showing what we did is we looked in animal brain and in human brain and looked to see whether those abnormalities were the same. And what you can see here is this cholinergic is those particular types of cells. Then in the mouse, there's a decrease in the red here, and you see also a very strong decrease in the humans in a similar part of the brain, whereas this other neurotransmitter, which is not involved, also looks more normal. So basically confirmed that what we're seeing in the mice, this specific neurochemical abnormality, also is present in humans. So again, we have this connection. And so we wanted to understand, how does this happen? And this was a little unusual because they're losing these cells, but the drug that I showed you, which actually helps these patients, blocks the action of those cells. So how could that be? If you lose the cells, you get the illness, but if you block them more, you actually help the illness. So for the interest of time, I'm going to skip over a few slides, but I'll just tell you the bottom line, which is it turns out that those remaining cells, by looking at the animals in different ways, those remaining cells become very hyperactive. So whenever you affect one part of the brain, it doesn't just, everything else doesn't stay constant. You know, there's a lot of action-reaction. So this has led to a completely new idea about what the cells are, how we have to attack them. And what we're doing now is looking to extend this to human patients using what's called PET imaging, or positron emission tomography imaging. And I'll just quickly jump to that last slide. 1 second. Let's just go here. Yeah. So this actually is, this is a picture of human brain using, it doesn't really matter the name of it, but it's a particular PET ligand that only looks at those cells in the brain that use this acetylcholine, this particular neurochemical. So out of the billions of cells in the brain, where you see red or yellow, that's where these cells live. And so what we're doing, and we developed this when I was at University of Michigan and was leading a Parkinson's Center of Excellence. We developed this and is now in use widely in patients with Parkinson's disease. Classically, people with Parkinson's disease, the problem is too little dopamine, but it's very clear that there are other neurochemical abnormalities. And so we're studying that in Parkinson's, and now we're going to use the same tool in the dystonia patients to look at them. And so I think it's also a nice example of when you develop a tool for one thing, it doesn't really remain limited to that. It can become broadly applicable across sort of various neuroscience questions. So in order to leave time for questions, I'm going to end there. I just always want to thank the people in my laboratory who do the really tough work, the funding sources, and I appreciate your attention. I'll be happy to talk with you and answer any questions that you may have.
Okay, if you're online, please add your questions to Q&A, and we'll try to get to as many as we can, but we'd love to open it up to questions here.
You're shy. Please. Sorry. Can I ask you about Alzheimer's?
Yes, you can.
So, as you know, the past 12 months there's been a lot of activity with monoclonal antibody therapeutics being developed to attack beta amyloid. What do you think about all this?
So what's being referred to, just let me step back and just make sure everyone's on the same page. So in Alzheimer's disease, actually in neurodegenerative disease generally, so in Alzheimer's and in Parkinson's and Lou Gehrig's disease, a common feature of these illnesses is the deposition of protein, abnormal deposition of protein. So you get clumps. I like to tell people, if you put bad milk in your coffee, you see the clumps, that's protein clumping. So you see that in the brain. Now, there are different proteins clump in different diseases, so I'm not saying they're all the same, but there's a kind of common theme. In Alzheimer's in particular, we've probably heard a lot about amyloid, and there's two. There's beta amyloid, and there's also tau, and those are two proteins, among others, that are the real proteins that aggregate in the disease. The monoclonal antibodies that are referred to is it's an antibody, like your immune system normally works. And the idea is, and there have been a lot of trials of these, is that if you can get these into the brain, they can bind to this clumping protein and help remove it or help prevent it to clump. And actually, incidentally, one of the reasons why this is, people think this is, or that's particularly interesting about this, is it's been found, and Mark Diamond, who runs the Center for Alzheimer's and Neurodegenerative Disease, his work really was, I think, arguably leading the way in understanding why does the disease spread? Actually, it's this clumping protein starts in one area, and it kind of jumps from cell to cell to cell. And so the idea is, now that it's going outside of the cell, this antibody could potentially attack it and slow it down, prevent it. What was very much in the press and which was being asked about is this trial of aducanumab. First of all, there have been a lot of failed trials of these antibodies. Aducanumab was one that was recently FDA approved, but it was approved against actually unanimous decision of the scientific board. And that's a sort of political question about the needs of, what kind of drugs should be made available based on what else is available and so forth. So I'm going to we can talk about that on the side, but just to more address what I think you're really asking is this a good therapy? Is this a good approach? I think there are a couple things that I want to say to make this clear. First of all, what's really clear now, and much more clear in the last 5 to 10 years, is that Alzheimer's starts probably 20 or 20 plus years before we actually have symptoms. So you may have symptoms, someone may have symptoms in their 70s, but this process may begin in the 50s. So one issue is that all of these therapies have been tried in symptomatic patients, and more through things like what I showed you about the biomarkers. Now we have much, much better biomarkers to detect people earlier, even before symptom onset, and to be sure that they actually have the disease and to give therapies at that time. So those haven't really come as much on board so far. But I think one issue of the failure has been probably the timing, or at least that's one possibility. There's also additional antibodies related, similar to aducanumab, that are trickling through now the pipeline that look like they do have potential symptomatic benefits. So aducanumab, even though that was so-called approved, it changed what it looked like in the brain, but it actually did not change the patient's symptoms. So that was another big point of contention. Should we be making something available that just changes a picture and doesn't actually apparently help the patient? So to put all of that data, that's a long-winded answer, but to put it in, I think one is, I do think that there's hope that these antibody treatments can impact the illness in a positive way. I think we're going to have to see which one and how early, number one. Second point is, almost all of them have been against the so-called amyloid, and almost none have been against the tau protein. And actually, there's a lot of data to suggest that tau may be the more important target. So I think there's hope, but there's a lot of work to be done. And then lastly, I just want to reiterate what I mentioned, which is separate than what you're asking, but the immune system appears to play an important role in that transition from the amyloid phase to the tau phase. And there's a lot of drug therapy coming along now targeted at that, and we'll just have to see how that plays out. So I hope that answers. Yes, great question. Great question.
So we also have some questions. Let me ask this question online, and then whoever, did you have a question? Let me just, is the deep ultrasound technology available for vocal tremor or head tremor?
So the ultrasound therapy right now has been limited to limb tremors. We have seen some impact on head tremor in some of the patients who we've treated that have limb and head tremor, because sometimes they come together. I would say we're a little bit in the gray zone at this point, and I think that for whoever that is, I would say whether it be here, if you're in Dallas, here at UT Southwestern, or if you're elsewhere, I think it's worth going and talking and exploring in your particular case whether there might be some comfort. One thing I would mention is, now we're getting into a little detail, but it's important to answer this question, is you don't just, people they don't just sort of zap a part of brain. Actually, the power level of that signal is sort of turned up to a point where it doesn't damage tissue, but it impacts its function. So actually, the way it works is they kind of gradually turn up the power, and if someone's having a tremor, they'll see, okay, now it's having a positive effect before they do any damage. So they're basically making sure they're in the right place and they're getting the benefit that they want before there's anything irreversible happening. And then, once they're comfortable based on all kinds of tests and so forth, only then do they do that. So one thing that people are thinking about now, but it's a little early days, is for these non-traditional kinds of tremors or other symptoms, is you may have to just get in there and see how is it looking, is the typical target going to help, and it may be they might abort or they might actually be beneficial. So I think you just need to talk. So it's a potential.
Yeah, and a follow-up to that question. Does the high-intensity ultrasound, does it work for all limb tremors, or is it just specific cases? And then the follow-up question is, are there possibilities of using this high-intensity ultrasound for other brain illnesses other than Parkinson's?
So, great question. So right now, the most common tremor that this ultrasound is being used for, and the one for which it's FDA approved and so forth, is actually something called essential tremor. It used to be called, tremor of aging and so forth. It's its own illness. It's an illness that's sort of like what I was talking about dystonia, like the genetic form has one symptom. This is a primarily tremor disorder. It's distinct from Parkinson. It's tremor. And actually, that's first and foremost. And we actually have the chair of our neurology department, Dr. Lois, and this is no over-exaggeration, he is the world's expert on essential tremor. So for those of you who might want to know that. It's also used for Parkinson, but in much more limited indications. And that's a more recent indication. That's essentially for people who have tremor that is just can't respond to medications, that don't respond to medications. To get to your larger questions, what about other tremors? Those really are on a case-by-case basis, and it very much depends on, there are many things that cause tremor. I would say the vast majority of what we're treating and what most people are treating is in essential tremor and these particular subgroup of patients with Parkinson. And as we get to other illnesses, we're more in an unknown zone. And that's part of what's being tested. There's certainly, actually getting to dystonia, there are things called dystonic tremors, a tremor that's caused by dystonia. And there is some work to suggest that may work. So I think we're on the road, so to speak. Now let me just go to your larger question, which I think is as important as that, which is, what about other illnesses? Right? So I think the answer is that's exactly the vision, is how else can we use this? Can we use it for things other than tremor? There has been a trial of the more cardinal motor symptoms of Parkinson, the slowness and things of that sort. The early report on that was not that great, quite frankly. But it's early days. And there's even a notion to use this in certain psychiatric conditions. Again, very early days and more theoretical. I don't want to give the wrong message. But the notion is that through brain imaging and understanding these circuits and how information's flowing, one, and two, the ability to go in there and not damage the brain, but to use it as almost a tool rather than a treatment. So if we could kind of reduce this area here, does this person's mania or things like that, does it go away? So that is the vision, and it's part of this larger umbrella of neuromodulation. The ultrasound is one thing, but I also want to point out that although it is more invasive, there's a lot of work being done on this DVS type things, that putting electrodes in the brain for not just Parkinson, but other psychiatric conditions. And actually, Dr. Paradian is very much involved in this for things like resistant depression, severe pain. So the playing field is large. I think it's just going to take some time to see which are going to pan out. But I feel very confident that some will. It's just hard to know where it would come.
Steve.
Yeah, real quick. Real quick. Yeah. With respect to the clinical side and the prevention side, how optimistic are you that the payers are going to start placing value on some of those preventive measures? Because in the world I came from, right, payer adoption really is important to kind of embrace some of those preventive things, because we know the cost on the other side.
You know what I think? I mean, it's hard to be optimistic when thinking about insurance companies, but I think if I just think about it, if I kind of take away the politics and all the money, I think we're going to have to show benefit. I mean, to be fair to them, I think we're going to have to show in randomized, controlled, multi-center trial, in a real way, we're going to have to show benefit. And I think, now I'm going to speak very much to the heart of what you all think about. I mean, I feel very strongly that how we live, being sedentary, being stressed, all of these things are, we brought some of this on, there's some societal pressures that are not good for our brains. I mean, that's just a fact. And so, but I think it's going to come down to efficacy. I mean, the little ray of hope I have, I mean, if you look in, for example, to the autism field, there has been legislation there, and there are things that are actually mandated for support because they showed that it made a difference. And also healthcare systems see that if you train patients and their families, again, I'm talking in this behavioral health area, how to deal with issues more, they don't end up in, as you say, they don't end up in the emergency room, they don't end up at your hospital, they don't, God forbid, commit suicide or whatever. And so I think it's going to be about effectiveness and really rigorous trials, ultimately.
So my question is actually a good follow-up to what you were just talking about. Can you make the connection for us between brain health wellness and brain health illness? And if you had a wish list around wellness, how would that link to the work you're doing at Southwest, UT Southwestern?
Well, I think it's a very strong one. Okay, I think that let's take Alzheimer's, which is a big gorilla in the room, right? Thinking memory. There's evidence. Let's start with simple medical things: hypertension, diabetes, smoking, years of school. All of these things are clearly linked to the likelihood of getting, let's say, dementia generally, not necessarily Alzheimer's, but it's dementia generally. The concept being, even if amyloid, and it is common in all aging brains, and it's going to take out X% of your ability for the brain to work. If you haven't harmed the rest of it through these other, especially vascular disease and by the way, exercise as well, the idea is you're going to be able to go further without being impacted by the pathologic process, right? So I think how we handle our brains, how we take care of our brains through those purely medical or largely medical things is a big deal. Now, beyond that, there are, and I'm going to come a little closer, there are very intriguing, and you guys will know a lot of this probably better than me, but there are very interesting reports to show that if you look at the size of individuals through true mathematical means, size of their social network, the rate of decline of cognition and memory reduces. This is serious, rigorous work. And so I think more and more we're going to have to be thinking about both sides. I mean, we are already, and we know that. But I hope that answers your question.
We call it left a boo. We need to get
left a what?
Left a boo. That's what Jeff Link says, like a military term. If we don't get people thinking healthier and doing some of these things to be proactive. So I'm going to ask one more question on that.
I mean, I just want to say that I tell all my patients this, I'm the most horrible exerciser in the world. I mean, I just don't like it. I wish I did. I just don't. But it really is a great medicine. It is, and I want to just say, in wellness, but also in illness, there's some very interesting work being done in immersive environments, virtual reality, where people can really become engaged for, instead of minutes, hours, in terms of promoting, now I'm talking about illness, restoration from stroke and other these kinds of things. It's early days, and we'll have to see, but these things are coming down the pipe.
One more online question. Lou from University of Florida. Is there any data or evidence that implicate neuroimmune dysfunction in the etiology of dystonia beyond epidemiology?
Okay, so neuroimmune and dystonia. So dystonia is, so I would say yes and no. So I showed you, you remember that mouse brain I showed, and it had red, and it's sort of the front half motor part of the brain. So, and you also remember that people with Parkinson's can get dystonia as one part of the constellation of their symptoms. So essentially, anything that damages that, what's called the striatum, this basal ganglia, essentially anything that damages it, whether it be an immune damage, like someone has encephalitis, a Parkinson, a stroke, tumor, anything that damages that can give the symptom of dystonia, of the abnormal movements. So in that case, in that sense, yes, indirectly it can cause it. But in these so-called pure forms that I'm studying, these genetic forms, there's no belief or no evidence that the immune system would be involved in that.
Thank you so much, Dr. Dauer. I know we have individuals here that have different motor disorders, PSP, some new Parkinson's diagnosis, and we are so excited to have you here in Dallas to be a world center on this. It's so important, the people that suffer, and I probably missed some individuals, but this means a lot to us to have you and your expertise, which is so, really incredible in terms of changing the way we look at things. So thank you for being here.
Thank you very much for the invitation and the opportunity. Thank you.
So please join us. Our next Frontiers is on addiction. USC's Francesca Philby, that you actually are working with on a joint grant, is going to be hosting. Yes. So we're going to be hosting that on December 2nd. Then on December 7th, our Brain Health Presents is on neuroscouting. How do you measure peak performance with individuals? And we've got neuroscientists from Boston. Mark Esposito will be here to work with how to calm the brain in the midst of chaos. They work with a lot of elite athletes. They are also part of our Brain Health Project. So if you come in and you do your brain imaging, part of that neuroscouting, you can see how you can change your brain. So the slide coming up to show what's next. Oh, and then you can scan for that. Anyway, thank you so much for being here, and thank you again to Dr. Dauer for being here.